Hello and Happy New Year. Welcome everyone to this English lecture series number 105, brought to you from Live Faculty of Engineering, University Technology, Malaysia. My name is Amir Zanadipour from the Institute of High Voltage and High Current, School of Electrical Engineering, Faculty of Engineering, UTM. First of all, I would like to thank Professor Datu Engineer Muhammad Rafiq, our Dean of the Faculty of Engineering, for excellent organizing and managing this lecture. For your information, this English lecture series, we invited prominent professors around the globe to share the knowledge, expertise, and experience, and perhaps to exchange ideas. I'm happy to invite our speaker today, Professor Antonello Monti from the RWTH Aachen University in Germany. Prof. Monti will deliver the lecture entitled Towards a Fully Digital Power Grid. So for those who know, Professor Antonello is a well-known professor in the field of the power system and power electronics. Without any delay, I would like to invite Professor Muhammad Rafiq, the Dean of the Faculty of Engineering, for further introduction of our speaker. Over to you, Prof. Muhammad.
Thank you, Dr. Amir Reza. Assalamualaikum warahmatullahi wabarakatuh. Welcome, everyone. Welcome to our 105th UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq, and I am the Dean of Engineering, University Technology, Malaysia. Today, it is my utmost pleasure to welcome Professor Antonello Monti from RWTH Aachen University, Germany. A bit about our distinguished speaker today. Antonello Monti received his M.Sc degree, summa cum laude, and his PhD in electrical engineering from Politecnico di Milano, Italy, in 1989 and 1994, respectively. He started his career in Ansaldo Industria and then moved in 1995 to Politecnico di Milano as assistant professor. In the year 2000, he joined the Department of Electrical Engineering of the University of South Carolina, USA, as associate and then full professor. Since 2008, he is the director of the Institute for Automation of Complex Power System within the E.ON Energy Research Center at RWTH Aachen University. Since 2019, he holds a double appointment with Fraunhofer FIT, where he is developing the new Center for Digital Energy in Aachen. Dr. Monti is author or co-author of more than 400 peer-reviewed papers published in international journals and in the proceedings of international conferences. He is a senior member of IEEE, associate editor of the IEEE System Journal, associate editor of IEEE Electrification magazine, member of the Editorial Board of the Elsevier Journal SEGAN, and member of the founding board of the Springer Journal Energy Informatics. Dr. Monti is the recipient of the 2017 IEEE Innovation in Societal Infrastructure Award. So that is a brief biography of our distinguished speaker. Here now is Professor Antonello Monti from RWTH Aachen University, Germany, with a lecture entitled Towards a Fully Digital Power Grid. Professor Antonello Monti, over to you.
Thank you very much, Professor Rafiq, for your kind introduction. It's an honor and a pleasure for me to be here today. And I will now share my screen to bring the slides. You should be able now to see my screen.
Yeah, we can
my slides.
Yep.
So, title as already anticipated, Towards a Fully Digital Grid. In my talk, I will summarize a series of activities that I've been involved in the last few years dealing with the digitalization of the power grid, which is basically the core of the research I'm doing here, both at RWTH Aachen and in Fraunhofer. When I started my tenure here in Aachen, the key buzzword of research was smart grid. If I think back when I started my chair in automation of complex power system, everybody was asking me, are you doing research in smart grid? This seems to be, at the time, the key element that was describing the most of the research in power systems at the time. But recently, I was involved in a document for the European Commission that was looking at the future of research and the needs in power system. And I played again myself this time, this word cloud game. And when I did this job, I realized that at the center of the word cloud now, we have the word digitalization. It seems like we had this change that the topic smart grid now evolved in the topic digitalization. But the question is, what does it mean? What do we mean by digitalization? And is just because we need periodically to change the hype, or did we realize that the question we are addressing is actually broader than what we thought when we were talking about smart grid? First of all, let's go back to a little bit of definition. What is digitalization? Digitalization is the process of moving to a digital business that is using digital technologies to change business models and provide new revenue streams and value-producing opportunities. This is a definition that goes beyond power system. And in reality, we can definitely say that many sectors right now are going through a process of digitalization. So that in that respect, energy is just one more. And what it means, though, going back to my original question, if you think about it, a digital energy network is a broader concept than smart grid. And I will try in the next few slides to explain why digitalization is broader than smart grid. So we were not going the wrong direction, or we didn't change direction, but we actually broadened up the challenge because we realized that we need a comprehensive approach that, for example, is not only technical, but also involving social component. What I just mentioned, this word cloud, came from this report that you can also download. Is now about 2 years old. And I was leading one of the task force producing this document that tried to understand what were the challenges in the power grid in Europe, so to shape the research for the European Commission. Here you find the link where you can, for free, download this report. What was critical in that report was to understand that using as reference the SGAM, the Smart Grid Architectural Model, which is the standard developed in Europe to define application in the smart grid, we actually define in that standard 5 layers, but to simplify in the report, we came up with 3 layers. One layer is the physical layer, one is the infrastructure layer, and one is the business layer. So if I go back to this original question, smart grid versus digitalization, I would say that normally people, when we're talking about smart grid, were mostly talking about what was happening at infrastructure layer, which means trying to make the grid smarter in the sense of adding sensor intelligence in the infrastructure. But when we look at what's going on in the grid right now, we realize we cannot forget the physical layer, which means there are fundamental changes that are happening in the system itself, which are affecting fundamental concepts that have been valid for about 100 years. So that is not just about adding few sensor intelligence in the infrastructure that will make the grid of the future, but we need a change in the understanding of the physical layer. But all this will be possible only if we involve the business layer. And when we involve the business layer means that this change is in particular bringing to the center of the system the customers who used to be just the peripheral element and now are the cornerstone around which we can build the energy system of the future. In that respect, you understand that we also have a socio-economical aspect of digitalization that we cannot put on the side. So we see now that this view of digitalization requires the intertwined analysis of these 3 layers to really understand what's going on in the grid right now. And when we put these 3 together, the real common term is digitalization. We are making the physical layer digital, we are building an infrastructure layer that is way more digital, and we need new business models which are possible only thanks to digitalization. But let's try to go back and think about the physical layer, first of all. Let me spend 5 minutes on history. If we look at the beginning, how the power system developed, we all know that started with a famous fight between two geniuses of the electrical history. They were Thomas Edison, and Thomas Edison was talking about building the power system using DC current, building systems from the bottom using small power plant and distributed generation. And on the other hand, we had George Westinghouse that was vice versa supporting the idea of using AC current, concentration of the generation, big power plant, moving to high voltage and lamping as much as possible generation. That brought to this famous world of current at the end of the 1800s. The result of this world of current is the power system that we know today. And the winner was basically George Westinghouse, also thanks to a cooperation with Nikola Tesla. They brought to the first significant power plant. Interesting, the first large power plant was actually a green power plant because it was an hydroelectrical power plant at the Niagara Falls. But why did Westinghouse win? What was the winning element? The winning element was the transformer. The key of this battle was exactly related to this power plant at the Niagara Falls to connect the first industrial site that instead of using distribution of power in the sense of mechanical chains, went to a distribution of electrical power. In doing this, they were connecting the Niagara Falls to Buffalo, New York, where this plant was going to be built. And it turned out that the best way to do it was to elevate the voltage close to the power plant, go in high voltage, and then transform it back in low voltage when we were close to the system. This was only possible because of the transformer. And that shaped the system. AC was the best option, mostly because we had a way to select the proper voltage level wherever it makes sense and to change it very easily and very efficiently thanks to a transformer. That brought to the idea of Westinghouse to be the winner, going to lamp generation, and to build a system then, thanks to this large power plant, in a way that is based on rotating masses that are able to smooth the transient, so to create a clear decoupling between the electrical transient, the electromechanical transient, so that the automation could run at a very slow time scale compared to what are the typical time constants of the electrical system. And that brought also to the system to be as interconnected as possible. If right now, one of the masterpieces, I would say, in this direction is exactly the Central European system, in which we have 27 countries interconnected to each other, synchronous with each other, to build a system that all in all together is extremely stable and robust and never experience a complete collapse. So we built everything around the AC idea. We built it around the concept of rotating masses driven by synchronous operation. And we had this clever idea that frequency is a main communication channel that allows us to understand what the system was doing. This was the key element around which the system had been developed for 100 years. But now, this was 100 years ago. That was, again, another view of the Niagara Falls plant. And if I want to take a representative of what we have today, I will come to this one. This is the new transformer, at least one new possible transformer. This is a DC-DC converter, multi-megawatt, medium voltage in DC. This is something that's been developed by my colleague, Professor De Donkeri, in his lab, and is part of some of the large research activities we have together in the field of what DC could do for the future. So what's going on is that now substituting electromechanical systems with electronics, we have a completely different scenario. And then we have to rethink exactly at the physical layer and put under discussion the critical element that define the automation, stability, and so on, because we have a complete new set of tools and then different principles that can be applied. I will give a very simple example. as part of a large European project called Reserve, we did some studies using the classical 9-bar system of IEEE, but we substitute the classical generation unit with renovation on renewables. What you see here in 3D is a graph. They show what frequency is doing. What this picture shows is that under transient condition, which is the constant situation of this system, we cannot talk anymore about a single frequency, but frequency becomes quite a local information that is changing all the time, and then giving one number representative of the system in a highly electronic system becomes extremely difficult. That shows that one of the cornerstones around which we build a system in the past is now under discussion, which means we need new definition at least of what is the system frequency if we want to use it in our system. And then you may wonder, is that something just simulation for the future, or is just something happening today? We have to distinguish between energy and power. We know we are struggling to reach the 100% carbon-free system, or at least a carbon-neutral system, and that the plan, at least for the European Commission, is to reach this goal in 2050. So that looks like 30 years from now. But interesting is that, well, first of all, the total contribution for renewables already today in Germany is reaching 40% last year. So this means that you have 40% all over as energy the year. We have moments in which the operation already happened with more than 100% energy coming from renewables, which means that we have moments that in Germany we can have enough generation for renewables to fulfill completely the loads. That's obviously not possible all the time, but actually a moment in which when we combine the generation assets that we cannot turn off and the renewables, we get way over 100%. We had moments in summer in which during weekend, particularly when the load is a bit lower, we had more than 50% energy coming from PV in low voltage. So this network with high penetration of electronic-driven system not only is the future, but is happening today. If I look from the point of view of the power system dynamics, if I look from the point of view of system automation. What does it mean? What does it mean as power system dynamics is we can put in a question of eigenvalues. So if I look at the classical power system, every book starts saying we have family of eigenvalues that become faster, starting from this lowest one. We have the thermal related to the power plant. We have the electromechanical systems that are the main dynamic with which the frequency control and deals with. And then we have the electromagnetics. We are too fast. And then we always focus on the blue one in the middle and trying to assume the electromagnetic always in steady state. And we consider that we have no chance to deal with the red one when we have to solve a problem in the blue region. In the future grid, or as I say, for many moments in the today grid, so let's call it modern power system, we should say thermal are gone and these other are mixed together. We have now to talk about power electronics driven eigenvalues. What does it mean? Again, is that a bad or a good news? I like to be positive and say this is a good news. And the reason why this is so broad in the slide is because actually now the eigenvalues are mostly something we can program, we can define, and how those dynamics evolve in time partly is totally human driven by the way we design the controller and how we program the behavior of the resources connected to the grid. Here an example. This is work not from me, but from a very good group in Norway, where they start looking at the concept of virtual inertia. So having an electronic system doesn't mean not having anymore the possibility to introduce dynamic in the system. And actually, the nice thing is that we can program the dynamics. We can make sure the control achieves specific eigenvalues we want because it becomes part of our result. Is part of our control, is not only the free response of the dynamics of rotating masses. The rotating masses were nice because they were smoothing the transit. Now we have the option to fit things together in the way we prefer. This is the main message. And when we do that, we can also completely change the paradigm. We can go beyond the virtual synchronous machine. The first idea that people had was, okay, what I can do now, programming, I emulate virtually the behavior of a synchronous machine. Synchronous machines are great, but they also have limitation because they have nonlinear behavior and other type of oscillation that can be induced by the interactions that the machine has with the grid. We can imagine something that is no one of the rotating machines that we have, which present characteristics, dynamics that actually are the best for us. So we come up with the idea that actually dynamics are now a degree of freedom, and we can actually make sure that this interaction between generations and grid, which traditionally described by the swing equations as a nonlinear behavior, could actually be linear because we program the behavior, and we can make sure that instead of having the curve between power and angle going with a typical sinusoidal curve, there can be a straight line playing with the voltage. Okay, this is just a diagram, but this can be put in terms of equation, determining now the system behavior as a dynamic in our new type of, we call it synchroverter, so inverter that behave as a synchronous connected system. We can do it in such a way that then the eigenvalue are known and valid for a wide range of points. So we moved from a system that used to be linearized around small operating point to the possibility to think very broadly and having written in stones the eigenvalue of the system in a quite broad range. This can be done on a single machine, but recently we demonstrated in a paper that with the same approach and our view of dynamic inertia, this can be built also for a multi-machine system. So it's possible, thanks to the smartness of the controller or the sources, to obtain a fully linear behavior for the system, which means the eigenvalues are known. We don't need to change for every change of the operating point, recalculate the so-called modal analysis to understand any possible risk of oscillation, and we built a solution that is valid for a broad range. And here you see how that happens. You see some transient in which we have been playing with the load and seeing the results. You see that the dynamical response is always very smooth, always the same eigenvalue, even if we change significantly the operating point every time. But there is also other alternative. What I show you so far is how the programmability of power electronics can be used to improve the behavior in AC systems, building a digital AC system. But we can also imagine that actually, as we are moving to a fully decentralized solution, Edison was right not only in that direction, but was right in thinking the DC is better. So it makes also sense to look at the advantage of DC, better use of material, higher efficiency rate, no need of worry about reactive power to build a system that will be totally based on DC. Of course, we don't change from night to day to night, from a full AC system to a DC, but there are a lot of possibility of technology insertion already today in which DC is making a better job. Here you see an idea, for example, instead of classical reinforcement of the grid and distribution, because that's where most of the work is going on, the reinforcement can be done with medium voltage DC lines, interconnecting substations so that we can use the redundancy of the line in different locations and better support fully electric homes, or also even more critical, the growing role of charging infrastructure. Same time, incorporating easily in every location also storage options that will be used to compensate for the volatility of generation driven by renewables, and creating those systems as interconnection of local networks as a stable and robust and self-balanced regions of the power system. A system that now, in this view, thanks to the insertion of DC, becomes more a bottom-up system than a top-down. This is not just theory. We have, as I mentioned before, a large project funded by the German government. We are building this experience in reality. We developed as long as I know, the first medium voltage DC multi-terminal grid in our campus, connecting several buildings. Right now, actually 3, sorry, but we plan to go to 4 very soon, actually 5 in a couple of years, and trying to develop and applying actually new theory on how multi-terminal DC network can be controlled and stabilized, inserted in the context on an available AC network. But that's not the whole story. As I said, one thing is the physical layer, but we have other layers. And the other layers, as I said, are possible only if we have better automation and we involve customers, which means that now we are also rediscussing how the grid, from the energy perspective, let's say before was mostly about dynamics, the very fast transient, let's say. Now let's think about keeping the system stable and balancing energy. We have been talking about a grid so far in which we have been playing, leaving the customer free and controlling generation to keep the balance. But does it make sense in this scenario with renewable-driven grid? It's clearly not the same, and it brings the focus that now the generation becomes the input and the customer becomes, or the customer side, where we have to find flexibility and controllability, which open up from the digitalization perspective, completely new topic of the role of the customers and the business model that can involve customers and how grid operator can access flexibility to make it work. And this is somehow the mix between the infrastructure smartness, that's what the grid operator does, the business models, which is the top layer I mentioned at the beginning. Flexibility is the big topic in this context. Currently available resource of flexibility in Europe, according to the European Commission, so what we can access is about 20 gigawatt. Theoretically, we could have already 100, but we don't have the way to access. But what is more critical is by 2030, so in 10 years, we need 160 gigawatt. So you understand why creating the condition to unlock flexibility and to create more flexibility is a key step to make the energy transition possible. What are the key ingredients? We are talking about keeping the grid stable. We are saying we need the customers, we need sensors, we need intelligence in the substation, we need to bring things to the control room. We have to create a network of data that makes the exchange among these players possible and create win-win conditions. This complicated interaction is what has been summarized by the European Commission in the Smart Grid Task Force in this diagram that tried to show in the one slide basically all the different players that will interact in the new system. And you can just by intuition see from these slides that this is not a trivial topic. We have several players interacting. We have new players in the system like aggregators. We have then to rethink a lot of elements, and as mentioned already several times, key element is the prosumer, which is the new term to indicate customers which have capability to be active customers as load and as generation at the same time. But if I look at the data exchange that I need, I've been in a recent document discuss what is the level of maturity, and what we see here is the only level of maturity 100% in the exchange of data between the market and transmission system operator. But there is a lot of work to be done at all the other levels. Whatever the arrow here is yellow, it means that there are options, but not fully standardized. At least we don't have, again, I'm referring to Europe, a common understanding across the all power system in Europe on how will it happen. And then much more work is due when the arrow is red. So we see that this digitalization that is here, linking the two other levels I mentioned, the infrastructure, and also the business models is still in a big phase of evolution. Coming to the infrastructure, an interesting development is given by how we bring the intelligence in the grid. And how can that be done? When I started my class on automation of compact power system, I basically like to fight against the terminology smart grid because it gives the students the wrong impression we had before, a dumb grid. What we had before was an extremely smart grid that could keep the infrastructure under control, simply operating at transmission level. All the changes we discussed so far are now putting at the center and making as one of the most important and critical elements the distribution grid. The distribution grid is intrinsically very different from the transmission one, and then we need to rethink what does it mean to make it smart, keeping in mind this difference. Before, when we had classical systems, we had no need of a lot of intelligence distribution grid because it was simply delivering the power from the node center to the load center, from the load center to the customers. Now, it's where most of the activity happens because the generation is embedded. But that means that we have to deal with an infrastructure way more complex. I gave you some numbers. Well, the transmission, I like to reference to my own country, origin Italy. The transmission system operator, Terna, the unique one in the whole country, deals with a network that is about 30,000 kilometers of line. Enel, that through the E-Distribuzione is the biggest distribution system operator, manages more than 1 million kilometers of line. Why? Because it's radially reaching basically every customer, so the complexity and lines length is totally different. Which means we need completely different solutions. We cannot just take the experience of transmission and bring it here, but we need to bring in completely different approaches. We need to have more distributed intelligence, and then we need to reach the edge. And here we have an interesting coincidence of technology, because while we are tackling this challenge, it's also the time we are doing the rollout of the 5G technology. In this project mentioned in slide, Sonia, working together with Ericsson, which is one of the provider of telecom technology, we look at how 5G can make this easy for distribution grid operator. And we realize that we have a set of ingredients that makes the solution possible. We need 5G for the capability of having intelligence at the edge, so that we can have the intelligence close to where the problems are. We have to be able to solve with low number of sensors compared to the kilometers of line, and also sensor at low cost. And we need to use more and more artificial intelligence, because a completely standard model-based solution will get too complex to run in the real life. And here you see what 5G can bring in that respect is the concept of edge cloud that allows a secure intelligence close to where the points of control are needed, and also points are secure because they can operate completely separate from the public network in a local scenario, so that you separate what is urgent and critical. So the traffic has to be extremely secure and local, and the traffic of data, the vice versa, has to be operated in a more open environment, interchanging data. But 5G is offering a very secure and flexible way to bring these solutions. On top of that, you need sensors, low-cost sensors, and here, from our experience, we have been installing some of the smart sensor in our campus. For example, working with the company Altea, we instrumented our own substation in our university. We equipped those with low-cost phasor measurement unit, completely developed in my institute, now installed in several grids to get more information from each sensor in the location. But anyway, being extremely low cost in comparison to what we call normally PMU, if you look of what you can find in the market. That's why we call them macro PMU, and those macro PMU are directly connected to the cloud, so that where the intelligence will be. This has been done, like I say, not only in our network, but we have been instrumenting in cooperation in some of the European project networks around Europe. This is an example. This is a very small substation box in Ireland for the grid of ESB, where we installed our systems and where we were able to learn a lot of what was going on in the low voltage grid. Here you see the digitalization of the infrastructure, the possibility for the operator to access in an easy way. This is a screenshot from an app that we created to access the state and information about the grid. And here is interesting because thanks to this process, the operator learned much more than they expected on what was going on in their grid, that before the monitoring was available and so widely distributed, it was not possible. And they realized, for example, that in some region of their network, the imbalance between the phases was way higher than the design, and that brought to losses way higher than they could forecast in advance. But that shows how creating a platform of data that are connected and then used becomes a critical element. Creating this solution is an element fundamental to reach out solutions that are compatible with distribution grid. We started this work in the project Sogno I mentioned before. Now we evolve in a next project called Platone, in which we added more elements on what
Sorry, I think we have the problem for connection. I think the professor already disconnected to the system. Maybe the internet has a problem. Never mind, it's okay. But we can waiting for the prof, and we'll be start to the rest the presentation. I hope the prof solving this problem. Just a moment, please. And I am sorry about this situation. So I would like to invite all audience from the Malaysia and the Germany and around the world to ask a relevant question. I will read the question from the Facebook comment, and you can connect to the Facebook of the page of the Facebook of the Faculty of Electrical, Faculty of Engineering, and you can ask a question by the comments in our page, and I will read the question for the Prof. Antonello. So we have to waiting, and I'm sure the Prof will come, and the presentation the rest slide. Before to start this webinar, so we have the problem with the connection, and the prof already solved and has been solved, and I am sure he will come again.
Can you see me? Can you hear me?
Yeah, Prof. It's okay.
Okay. Now
it's okay. You can share the rest of your presentation. It's okay.
Yeah, I connect with my iPad, but on the iPad version, I don't see the way to share my screen.
Mm-hmm.
Do you know if it's possible?
If
I don't see the sharing
if you
screen
have
on the
your
iPad.
file, yeah, you have your file on your.
What I can do is to send you a link to my presentation, and you run my slides, and I finish my presentation that way. Because my computer is reset and I'm sorry, automatically started.
It's okay, Prof. It's okay. We can waiting for your presentation. Just I think around 1 minute. Need to 1 minute waiting for go up your Windows. Is okay.
No. The problem is the computer, the one where I was doing presentation, started automatically an update, which I didn't program. I don't know what happened.
Oh.
And so it's completely blocked. So I'm now connected with my iPad. What I can do is to give you a link to my slides, and then I will ask you to change my slides yourself. So you share the screen and I talk. Would that
Yeah,
be
sure.
okay?
Yes.
Sorry.
Yeah, you can send your slides to my email.
Okay, I'll do it in immediately. Just a second. I'll put you. Oh, no, okay. I'll send you by email. Okay.
Yeah.
Done.
Okay, you sent already?
Yeah.
All right, let me check. All right, okay, got your email and the link. Let me click the link. All right, okay. Right, okay, let's download. Okay, the file is downloading, just a few seconds left. All right, okay, downloaded, show in folder. Hang on. Open file. All right, okay. Can I have this slide number, Prof?
Don't remember which one was. Scroll and I will tell you. It should be around 30, I guess.
Yeah. Yep. Hang on. All right. Okay. Hang on. Let me share.
It should be not far away from the end, by the way.
Yep. Okay. Let me move Amiriza. Share screen. Share.
That's coming.
All right. Okay.
Yeah, we were down more slides. So 26 was done, I remember. This was done. Next, done. This was done
Yeah, this is the end.
before. Yeah, here before this one. I'll go
Before,
up.
yep. Okay.
One more behind again, 32 or 31 probably. No, one before. Yeah, okay, here, perfect. Yeah, also here. So
Okay.
I think if I know exactly where I stopped talking, I was talking about this other project where we added more element to the concept of platforms, having two key points added. And the main point that we added is the link to the customer, which I mentioned from the beginning is one of the key elements for the digitalization of the power system. And that happens here in our architecture thanks to a blockchain layer, which allows us to collect data from the customers in a secure way. The other element that we added is the capability to bring this data to a market platform, which the idea is that customers not only can provide data, but can access also market. And that's exactly the point where you see the link between the infrastructure digitalization and the definition of a new business model. Customers now become not just the guy paying the bill, but somebody that can be involved in any kind of market operation and then becoming definitely an active player into the system. Next slide. Yeah, here is a different view of the same concept. You see the blockchain interface at the bottom, the link to the market platform. Another important point, we organize this digitalization platform in a way that is not in contradiction or in competition with the systems already there, but with the capability to extend what we call legacy systems. So whatever kind of software that was already available using standard SCADA solution in the grid operator level. Next slide. One key element in all these efforts in defining data platforms and then this digitalization of the infrastructure is that everything we are doing is being developed as an open source solution. This is a key element because this is a too complex challenge for one single company to find a solution, or also for a single university. The cooperation, worldwide level cooperation is critical. For that reason, just last month, our concept of data platform has become a Linux Foundation energy project, and we built a worldwide community that can access our platform for free, and it can contribute to this platform. Everybody can access our code, everybody can join the Linux Foundation Energy and becomes an active player in this context. Similar other exercise mentioned here in this slide is the fiber platform, which is more oriented towards smart city, which allows us to integrate smart energy in the bigger picture of interaction that we call smart city. Again, a set of software tools which are offered completely as open source. Open source is a new paradigm for power systems that have been brought by digitalization, which is tremendously reducing the time of development of new solution and benefiting from the cooperation worldwide between experts from industry and academia together in developing pre-competitive version of solutions that company can customize. Open source doesn't mean that there isn't a business model. Actually, as Linux itself shows, you can build very solid business models around open source. Next slide. And that allows me to bring in a general picture what is the view right now of digitalization, data management at European level. Since last year, with the new European Commission, we had a law called Green Deal, which says that this transition to a clean energy system is not just a wishful idea in Europe, but is a law. So now we have a commitment from the government we never had before. Click further. And this means that digitalization in the energy system is a change within the change, and is not only technical, as I mentioned several times. And then opens the question of how ready we are. We have several challenges to make the whole picture working. We need data models, we need architecture, we need business model, we need governance and sector coupling. As you see from the little faces at the bottom, not in every sector, in every part of these challenges, we are at the same level of evolution. As you see, for example, governance, how all this idea of data platform will run is something which a lot of work still has to be done. And the new other, a very critical topic that is emerging is sector coupling, which means the electricity alone will not make it to build a full energy, clean energy systems. And that's why sector coupling, probably also in Malaysia, I'm pretty sure you heard the growing role of interest, for example, for hydrogen, but definitely linking electricity to other sector is a key element to make the transition possible. Next slide, please. And in building this picture is a very complex process. Here, I simplify this challenge in the 3 levels of customer, distribution, and transmission. And you can click further. There are several projects here, I don't enter in the details, that are trying to contribute to shape this picture. One more click. And in particular, last fall, so in October 2020, we started a project called Onenet, in which everything I told you so far should be harmonized to provide solution that we can call European solution. Next slide. Onenet is a massive project in which we tackle digitalization, the infrastructure and business model, new market definition in a very wide sense, very much at European level. We have 72 partners from industry and academia working together. And from the map on the right, you see the country where there will be experiments connected to this project. We are basically tackling, a good part of Europe. So it's not just a project in which we have a small demonstration in addressing digitalization, but we are really tackling what digitalization means for the whole Europe. Next picture. But to complete the same challenge I told you so far is not only for the operation, but is also for simulation. And how we have the distinction between the classical power system with the 3 different sectors of eigenvalues. You can click further. The same in simulation, we have to rethink and consider that in a modern power system, because those dynamics get together, you can click further, we have, again, the similar concept. And here is emerging new methods of simulation that will support the studies that we need to understand the complex picture we had before. And here we are using new solvers based on so-called dynamic phasor, but better to say, we use the frequency sweep, the frequency shift analysis as a way to address simulation in a new way. You can click further. The idea is that to find a way to address this new eigenvalue on the power electronic systems, we don't try to solve calculating the complete oscillation, but we can basically look at the envelope of the system. But thanks to the solver we built, we are able with the same model to build the envelope, but also to reduce the time step and follow the oscillation whenever is needed. So we build a tool that is able to adapt with the same model to the details of analysis that may need in different moments of performance simulation, while making the system faster whenever that is possible, but not switching model, but the model that can self-adapt depending on the challenge. You can click further. And yeah, here you see this idea one more time. The classical analysis done in power systems with the electromagnetic transient simulation and the frequency shift analysis or phasor domain, dynamic phasor domain, in which we don't follow the oscillation, but we look at the envelope. But still, we are able to go back to reconstruct. And here you see some, no, you can go to the next slide, it's fine. Here you see some very trivial examples in which to show that we don't need to know exactly the frequency of the carrier. Here we run the simulation with a frequency shift of 50 Hertz for a 60 Hertz network, but we are still able to run with time steps that are wider than what is possible in classical EMT analysis, making the analysis more efficient, still tracking more dynamics component that in the classical electromechanical analysis type. Next one. Yeah, can shift further. These are set of example of application, and you see how at the same time step, this type of analysis is much more accurate than classical model on EMT. Next. Same can be applied to power electronics. Here you can see the analysis of a switching systems and reconstructing also oscillation. We need more fundamental frequencies, but still the system is possible. In conclusion, and this is really the last chapter, all that changes also as we are academics, big effect on education. People talk a lot about the fact we need to bring together power systems and information technology. What I like to stress that actually there are three pillars, because power electronics is quite different from power systems. And the culture of people in power electronics is very different. So it's a triangle of knowledge that we need to tackle future power systems. Okay, go to the next one. We are doing this also in projects that are developing new education concept. One is the project Asset, in which we are developing also new models which are publicly accessible. So you can follow the link. Also, if you're interested to know more about the work we are doing to change education, to track the changes that are happening. And going to the next slide, we are also doing a broader effort working with many partners around Europe to define a so-called blueprint agenda for Europe, defining the education for digital energy. It's time to completely rethink programs in power systems to be able to capture the challenges that I tried to summarize in my slides. And with this blueprint, we will collect the key guidelines to help everybody. It will be mostly in Europe, but those documents will be public and can be used by also other countries all around the world to understand the challenges that we are facing in education. Next slide. Yeah, I reached my conclusion. I tried with my presentation to give you an idea of what digitalization means for power systems. I would like to approach this in an optimistic way. There are new options. There are not only new problems. We have new concept of operation. We need, though, open standards, also from the software perspective, to allow more interaction and cooperation. Here you see logos of some of the key projects that are funding, and mostly these projects are actually all of them funded by the European Union. You can find the website of these projects and learn more. If you're interested in, there are a lot of documents which are open and you can download for free. And in particular, going to the last slide, everything we do in the software domain, we make it open source. The simulation platform I mentioned before, DPSIM, is available as an open source. A lot of other tools we are developing the same. Here you have a website that is a Verein, so an association that is connected to the research in my institute, which maintain this website and distribute the results we have as open source, so that we do this to increase cooperation. We'll be very happy that after this presentation will be interest for anything of what we are doing that we offer as an open source, and you will be interested to use and work with us. And everything you go there, you can find, download, and play with it. It would be our pleasure if people use software we develop in another academic institution, or also in industry, if there is interest to develop cooperation. I thank you very much for your attention. I think this is the last slide. I apologize for the glitch in the middle that my computer got crazy. But thank you for the support. So we were able to finish anyway in a reasonable time, the presentation. And of course, now I'm ready for questions.
Welcome. Thank you so much, Professor Antonello, for your amazing and informative lecture. And I would like to invite all audience from around the world to ask the relevant question in Facebook as a comment to Prof. Antonello. So I can start with my own question. Actually, Prof, I want to know if we need to intelligence system to more secure and the more flexibility and of course the more accuracy, what technology you suggest? I want to know about the blockchain technology. Can help to this, or you suggest other technology?
We are learning about it. So we are, as I mentioned in one of these projects, Platone, we are looking at using blockchain to connect customers in a secure way to the power system so that we can trust the source of data. In cybersecurity is much more than blockchain. Let's put it this way. Blockchain is an interesting technology. Unfortunately, many times there is confusion between cryptocurrency and blockchain. And these are two different things. We are not dealing here with cryptocurrency. Here we are dealing with the possibility, and that's the fundamental of distributed ledger technology, to keep track of how data are brought into the system so that you have signatures on the data. And this is critical to be sure that you know if nobody modify or touch your data when you're working on automation solutions. So that's one use case. Of course, there are other use cases in which blockchain can be useful, like trading markets between peers. Again, that's an opportunity for customers. We have in Europe a lot of interest in the so-called citizen energy community. So the possibility for customers to interact with each other and have local markets. In all those use cases, blockchain plays a good role. But when we talk about the global automation, we need much more in terms of cybersecurity. I mentioned before some of the elements of cybersecurity intrinsic in 5G. So it's not the holy grail solving all the problems, but it's an interesting ingredient. That's the way I would put it.
Thank you, Prof, for your reply. I think we received the question. I appreciate our team show the question to Prof. Antonello. No, not yet received any question. Let me to check. I hope the audience after see this webinar will be asked a question more. Everyone is okay? So thank you so much, Prof. I think due to limited time, we have to finish this lecture. And if the viewers have more questions, can just email later. I believe the Prof. Antonello is happy to answer the question.
Sure.
So thank you again, and I hope to see you in the next DLS. And now I give back to Prof. Rafi for closing remarks. Over to you, Prof.
Thank you, Amireza, for sharing the session and for introducing Professor Antonello Monti to me. And to our distinguished speaker, don't worry, Prof. It happens. So the the glitch in between, it happens before, and that's the thing about technology. You know, if you if you rely too much on the technology, then somehow it happens. This kind of stuff. But anyhow. Thank you so much for accepting our invitation to speak at our UTM Engineering Distinguished Lecture Series, and to all our viewers worldwide. So we have more than 200 viewers watching this webinar. Thank you so much for watching UTM Engineering Distinguished Lecture Series. Do stay tuned because we have many more interesting lectures for you. Until next time, bye-bye for now. Bye-bye.
Bye-bye. Thank you so much.
Thank you. Bye.